Hello everyone, this video series mainly provides detailed explanations and comprehensive insights into integrated circuit layout design technology. Currently, this is the 2.0 version of the series, which has been thoroughly updated and extensively supplemented based on the 1.0 version. We hope this video can serve as a valuable resource for both aspiring students who are learning layout design technology and experienced engineers engaged in layout design. The main reference books used, firstly, The Art of Analog Layout, and secondly, IC Mask Design Essential Layout Techniques. This series covers 7 main topics. First, we'll briefly introduce some basic knowledge for layout design. The second part will explain some basic layers frequently used in layout design, along with their usage methods and precautions. We'll also discuss circuit failure mechanisms caused by defects in layout design. Thirdly, we focus on how to design the layout of basic circuit components including MOSFETs, capacitors, and resistors. The fourth and fifth are the core content of this video series and are crucial for layout design, especially in analog integrated circuit layouts. Fourth is matching, fifth is noise, sixth covers the overall layout arrangement and ESD, electrostatic discharge protection. Finally, we introduce the characteristics of digital integrated circuit layouts. This series mainly focuses on analog integrated circuit layout design, but also touches on some characteristics of digital circuit layout design for layout reference. Now let's start with an introduction to layout design. First, let's understand what an integrated circuit is. An integrated circuit, also known as a monolithic integrated circuit or IC, is what we commonly refer to as a chip. It integrates various electronic components and circuits into a very small, thin slice made of semiconductor material. This semiconductor material is usually silicon. On this thin slice, there are a large number of very small components called field effect transistors, which we refer to as MOSFETs. The photo in the lower left corner shows a chip. The black part around the chip is the packaging, also called the package. The middle part is the actual chip, which is also referred to as a die. The pins on the chip are connected to the package using gold wires, and the package has metal pins that connect to external circuits. The die inside is actually the chip that we cut from the silicon wafer, and its design blueprint is what we call the layout. The layout on the right shows what it looks like. It has various colors and many structures within it. On this very small thin slice made of semiconductor material, which is usually silicon, there are a large number of very small components called field effect transistors, or MOSFETs. The photo in the lower left corner shows a chip. The black part around the chip is the packaging, also known as the package. The middle part is actually the chip itself, which is also referred to as a die. The pins on the chip are connected to the package using gold wires, and the package has metal pins that connect to external circuits. The die inside is actually the chip that we cut from the silicon wafer, and its design blueprint is what we call the layout. The layout on the right shows what it looks like. It has various colors and many structures within it. Let's take a closer look at what it contains. The layout of an integrated circuit defines the geometric shapes used to process the integrated circuit on the photomask. Typically, the photomask is multi-layered, and processing an integrated circuit requires many steps of photolithography. Each step of photolithography requires a mask, and each mask corresponds to a specific layout pattern. Therefore, when we design a layout, it is definitely a multi-layered drawing. Looking at this diagram, the different colors represent different layers of the layout. So, different colors indicate different layers. The die inside is the chip we cut from the silicon wafer, referred to as the layout. The layout on the right shows what it looks like. It has various colors and many structures within it. The layout looks like this, filled with a variety of colors and numerous structures. Let's take a closer look at what it contains. The layout of an integrated circuit defines shapes to process the integrated circuit on the photomask. The photomask is multi-layered, requiring many photolithography steps. Each step of photolithography requires a mask, and each mask corresponds to a specific layout pattern. Thus, designing a layout is a multi-layered drawing. In this diagram, colors represent layout layers, so different colors indicate different layers. Now let's examine in detail what this specifically includes. The layout of an integrated circuit specifically defines the geometric shapes used for processing the integrated circuit on the photomask. Typically, the photomask is multi-layered, and processing an integrated circuit necessitates many steps of photolithography in various stages. Each step of photolithography requires a mask, and each mask corresponds to a specific layout pattern. Therefore, when we design a layout, it is definitely a multi-layered drawing. Looking at this diagram, the different colors represent different layers of the layout. So different colors indicate different layers. This is important to understand as we proceed in our discussion. The method we essentially utilize is through our foundry, which processes the templates based on the designs we create. The number of templates used depends on the steps of the process, right? Those process steps also affect the cost of our chips. The more layers of templates you use, the higher the cost will be. You can see that different layers have different colors, and they ultimately overlap. When we design the layout, we look at these layers from a top-down perspective and different layers represent different grinding plates. Essentially, it reflects a three-dimensional structure of the chip through a flat design. For example, when we stack all the layers together on the left, the layout looks like this, with many colorful details. In reality, there are many layers, and when we open it up, we can see all these layers, such as our N9, the active area, polysilicon, N-type doping, P-type doping, and so on. This is just a simplified representation of many layers. There are even more layers. So, when we merge all these layers together, we form the shape of the layout. Our layout design is about using these different layers to create the collective shapes of the grinding plates, which reflect the three-dimensional structure of our chip. When designing the layout, we must follow the design rules of the process we are using. For instance, if we are designing a layout using ZTE International's 180 nanometer process, we will refer to the design rules specific to that process. These rules detail the constraints for each layer of our layout, and we will discuss the specific constraints later. Now, when designing layouts, we will encounter two types of circuits. One is called digital circuit, and the other is analog circuit. When we design the layout for digital circuits, it mainly affects the speed characteristics of the circuit, meaning it influences how fast or slow the circuit operates. Therefore, when designing the layout for digital circuits, we usually focus on how to reduce signal delay or perform some matching. More importantly, we want to minimize the area of the chip. The area of the chip directly relates to its cost. If you can achieve the same functionality while consuming less area, it means you can produce more chips on the same wafer, which lowers the cost per chip. This is what digital circuits focus on. Now let's look at analog circuits, which are completely different from digital circuits. The quality of the layout design for analog circuits can significantly affect various aspects, particularly the speed characteristics of the circuit. More importantly, it impacts the circuit's precision. In other words, if an analog integrated circuit is not well designed, it can noticeably affect the circuit's accuracy. Why is that? The reason is that when we draw the layout, we must pay attention to several issues, such as symmetry, device matching, reducing parasitics, minimizing offsets, and avoiding signal crosstalk. We also need to optimize the interconnections. If these factors are not well considered during the layout design, there's a high chance that the characteristics of the finished analog circuit layout will deviate significantly from what you expected once it's fabricated. As for how we can avoid these issues or address them effectively while drawing the layout, we will discuss these problems in detail later in the video. Lastly, it's essential to treat your analog circuit as a work of art. In other words, the layout of an analog integrated circuit, once completed, should resemble an artistic piece. Why do I say this? Because the layout of an analog integrated circuit must consider many factors like matching, symmetry, and isolation, which results in a clear structural symmetry in the layout, making it visually appealing. Generally speaking, there's a saying that a well-functioning layout of an analog integrated circuit must also be aesthetically pleasing. If you look at a layout and it appears chaotic, you can be sure that the characteristics of that analog integrated circuit won't be great. Therefore, it must be treated as an artistic work. Now let's visually compare analog integrated circuits with digital integrated circuits. On the left, we have a digital IC, and on the right, we have an analog IC. If you look at the digital integrated circuit on the left, you can see that it appears quite chaotic, lacking any apparent regularity in the arrangement of components and wiring. However, there are still some underlying patterns, which we will discuss later, but overall, it seems to lack symmetry, with wires crisscrossing everywhere. This doesn't affect the functionality of the digital circuit. The layout is more concerned with minimizing area while ensuring the smallest signal delay or matching. Now, looking at the analog circuit, it's quite different. You can see that it has a well-defined structure with good symmetry and regularity. For example, the components are neatly arranged, showing a high degree of symmetry and repetition. This is a characteristic of analog circuits. Why does it have this characteristic? It's because when we design the layout for analog circuits, we need to fully consider factors like matching and noise. By taking these factors into account, the structure of the circuit tends to be more organized, which enhances the performance of the analog circuit. To achieve a certain level of matching, we might sacrifice some area, but this sacrifice is necessary to ensure the circuit's performance. Alright, let's take a look at what we call the tape-out flow. Tape-out refers to the process where we take our design ideas for the chip and ultimately fabricate the entire thing. We call this process tape-out, right? So what does the tape-out process look like? Let me give you a brief introduction. First of all, let's take a look at the entire process, which is actually divided into two parts. One part is completed in what we call a design house or a design company. In this design company, they create the actual design blueprint for the chip. This blueprint is then handed over to the foundry, which is responsible for manufacturing the chip. Currently, most chip designs are done using a combination of design houses and foundries. It's quite rare for a company to merge the roles of design house and foundry, meaning they both design and manufacture. Such companies are few and far between, but there are examples like Intel, which designs its own CPUs and also manufactures them. These companies are quite large. For the majority, design and manufacturing are separate. The design company completes the chip design, and once that's done, they have a blueprint for the chip, which is the layout. This layout is then handed over to the foundry, such as TSMC or ZTE International. After receiving the design blueprint from the design house, they continue with the manufacturing process. So what is this design blueprint? It's our layout. The interaction between them relies on a file called GDS2. Let's take a look at the overall process. First, the designer has an idea, right? They want to achieve a certain function with the chip. This idea first needs to go through something called circuit design. Whether it's analog circuits or digital circuits, you need to design the circuit first. So, circuit design is the logical layer, meaning that after connecting various components, whether they are transistors or logic gates, you can realize your idea. After that, we need to turn the design circuit into a manufacturable blueprint, which is essentially the layout design. We use a multi-layer drawing method to convert the design circuit into a layout. Once the layout design is complete, it generates a GDS2 file, which is the format most commonly used today. This file is then delivered to the foundry. So, the key link in the data handoff between the design house and the foundry is the GDS2 file. Typically, when we deliver the GDS2 from the design house to the foundry, this process is known as tape-out. However, once the foundry receives the GDS2, they definitely need to perform some checks. Even though the designers follow certain design rules when creating the layout, the foundry has to do a final check to ensure that the GDS2 complies with their manufacturing rules. If there are any issues, they will provide feedback to the design house, saying, "There's a problem, you need to modify your GDS2 and regenerate it." This process continues until both parties confirm that the GDS2 is correct. Once that's done, the foundry will generate a new file for manufacturing the photomask. The GDS2 will be used to create this new file, which is essential for the photomask fabrication. After the foundry generates the final photomask blueprint, it needs to be sent back to the design house for a remote check to ensure that the graphics in the blueprint are correct and that there are no missing layers. This process is called job view. If any layer issues are found during job view, we may need to go back and correct our GDS file. If everything is okay, then the photomask will be sent for fabrication. Typically, photomask fabrication is handled by another company, which the foundry will contract to produce the photomask using the generated blueprint. Once the foundry receives these photomasks, they can proceed with IC fabrication, including the photolithography process. After going through several steps in the chip manufacturing process, we will end up with chips. If everything is functioning correctly, these chips will reflect our original idea. For example, if our goal was to create an analog to digital converter, ADC, after this entire process, we should have a chip that can take an analog signal as input and output the corresponding digital signal, completing the AD conversion. So, this is the entire tape-out process. In order to ensure clarity, it is important to note that the GDS2 file is a critical component in the data handoff process. Specifically, the GDS2 file serves as the primary link between the design house and the foundry. Furthermore, the tape-out process is a crucial step in the overall manufacturing process. Moreover, the foundry must perform checks to ensure compliance with manufacturing rules. In addition, feedback is provided to the design house if any issues are found. Consequently, the process continues until the GDS2 is confirmed to be correct. Ultimately, the foundry generates a new file for photomask fabrication. In conclusion, the entire process is essential for successful chip manufacturing. So, I would like to explain a concept known as optical proximity correction, which is often abbreviated as OPC. Now, what exactly does this entail? Essentially, to put it simply, the geometric patterns on the photomasks we use for chip manufacturing are extremely small, as you might already know. These patterns are incredibly small, and they are indeed very tiny because, as you are aware, our chips are densely packed at the micro or even nanoscale. So when these photomasks are utilized to process the intricate patterns on our wafers, there are certain issues that arise due to phenomena such as diffraction and the non-ideal nature of the optical system. The optical system is not a perfectly ideal system, which leads to some unavoidable problems. It means that when we use the photomask for lithography, the patterns that get transferred onto the photoresist are not completely identical to the patterns on the photomask. They are not exactly the same, right? The entire lithography process involves using the photomask to transfer the pattern onto the photoresist. To be more precise, we apply this pattern to photoresist, then transfer it to the wafer. However, optical system imperfections cause pattern mismatches. This causes circuit shape mismatches. For instance, consider our layout design. It includes various shapes: long, short, L-shaped, squares. During lithography, optical flaws and diffraction cause pattern imperfections. Thus, wafer structures deviate from design intent. Originally, I designed a rectangle, but its edge is curved. The middle rectangle, meant to be uniform, varies in thickness. Photomask patterns differ from layout, causing circuit issues. Our design pattern and layout have regular shapes, but optical limitations cause deviations. Wafer structures don't match design. Rectangles curve, widths vary, shapes shrink or vanish, affecting circuits. OPC adjusts patterns to align post-lithography with design. OPC alters layout to compensate optical flaws, achieving closer match. This layout features various shapes: long, short, L-shaped, and small squares. During lithography, optical system imperfections and diffraction can alter the photoresist patterns, causing deviations from the original design. For example, a designed rectangle may have curved edges, and a consistent width rectangle may vary in thickness. Some shapes may shrink or disappear, affecting circuit characteristics. Optical proximity correction, OPC, addresses this by adjusting patterns computationally to better match design expectations post-lithography. After OPC, the layout deviates from the initial design to compensate for optical system flaws, achieving a closer final pattern. In job view, patterns undergo OPC, so while shapes resemble the design, variations in flatness or width may occur. These changes are OPC's necessary adjustments, not data issues, ensuring the final pattern aligns with the design intent. Without OPC, significant output losses could occur. Then, in these two shapes, one has become very small, right? And one has even disappeared entirely. For example, this one has just vanished, right? This can lead to the characteristics of the circuits we produce being different from what we expected. So, what can we do about this? That's where something called OPC, or optical proximity correction, comes in. What does it do? It actually modifies the patterns we've drawn using computational methods, making adjustments so that the corrected patterns after lithography will align more closely with our original expectations. This is the function of OPC. However, you can see that after OPC correction, the layout pattern has deviated from our initial design, but this deviation is precisely what compensates for the non-ideal factors of the optical system, allowing us to achieve a final pattern that is much closer to what we intended. So that's OPC. Why is this important? Because when we work with JabView, the patterns in JabView are all processed through OPC. So if you get a chance to work with JabView, you might notice that while the overall shapes are generally the same as what we designed, there can be some variations in terms of flatness or width. Some people might wonder if there's an issue with the data because what I originally drew looks different in JabView. For example, I might have designed a certain shape, but in JabView it appears less regular. However, this is actually the result of OPC at work. The changes are not a problem, they are necessary adjustments made by OPC. These irregularities help compensate for the non-ideal characteristics of the lithography system, ensuring that the final processed pattern reflects our original design intent. Otherwise, if we just used the original pattern without any adjustments, we could end up with significant losses in the final output. So, this is what OPC, or optical proximity correction, is all about. Why is it important to emphasize this? It's because when we work with JabView, the patterns on the photomasks in JabView have all gone through OPC, which is a critical process in semiconductor manufacturing. So, if you get a chance to work with JabView, you'll notice that while the overall shapes are generally the same as what we designed, there can be some variations in terms of flatness or width. These variations are not random, they are carefully calculated adjustments. Sometimes people might wonder if there's an issue with the data because what I originally drew looks different in JabView. For example, I might have designed a certain shape. But in JabView it appears less regular. However, this is actually the result of OPC at work. The changes are not a problem. They are necessary adjustments made by OPC. These irregularities help compensate for the non-ideal characteristics of the lithography system, ensuring that the final processed pattern reflects our original design intent. Without OPC, the lithography process would not be able to accurately reproduce the intended design, leading to significant deviations. Otherwise, if we just use the original pattern without any adjustments, we could end up with significant losses in the final output, such as reduced yield or performance issues. That's why OPC is crucial. It ensures that the final product meets the high standards required in the industry, maintaining the integrity and functionality of the semiconductor devices. Next, I'll introduce the design process of digital integrated circuits and analog integrated circuits. First, let's take a look at the design process for digital integrated circuits. The process goes like this. It starts with layout design, followed by logic design. Logic design, in essence, involves writing Verilog code to describe the circuit's functionality. So, the Verilog code is basically a way to describe our ideas in a language format. It serves as a bridge between our conceptual understanding and the physical implementation of digital circuits. By using Verilog, we can articulate complex logic designs in a structured and standardized manner, which is crucial for further processing. After we write it out, we move on to logic synthesis. The purpose of logic synthesis is to convert the functionality described in Verilog into a gate-level netlist. This means that what was originally a language description can now be translated into a circuit structure made up of actual gates, which can perform the operations we initially described in words. Logic synthesis is a critical step because it ensures that the abstract logic is accurately represented in a form that can be physically realized. After logic synthesis, we proceed to the layout phase, where we arrange these logic gates on the chip. This process is handled by EDA software, which automates the complex task of placing and routing the gates efficiently. The layout phase is essential because it determines the physical arrangement of the components, which affects the performance and manufacturability of the chip. Once the layout is complete, we perform a timing check. This timing check is mainly to ensure that the arrangement matches our original logic design. When we described the logic using Verilog, it didn't include specific physical components, so it was in a very ideal state. After adding these logic gates, we now have physical components to consider. We need to check if this layout can still meet the original functionality. Timing checks are crucial because they verify that the circuit will operate correctly at the desired speed. If it doesn't pass the check, we need to modify the Verilog file or redo the logic synthesis and flow planning until the checks are successful. This iterative process ensures that the final design is both functional and efficient. Once it passes, we move on to the routing phase. Routing involves adding the actual physical properties of the gate-level circuit layout and connections. This means we're creating a preliminary layout of the digital circuit. Routing is a complex task that involves determining the optimal paths for electrical signals to travel between components. After that, we perform another timing check to see if the layout with the real components still meets our original logic. If it does, great. If not, we may need to iterate through the process again. This ensures that the final product meets all design specifications and performance criteria. If everything is satisfactory, we then enter the GDS2 generation process. To go from layout to GDS2, we need to add something called a digital library. This digital library contains the layout information for the gates we used in the routing phase. Each gate is treated as a black box, which describes the physical properties of the gate-level circuit, but doesn't include the actual layout structure. We need to bring in the real layout structure for each gate, which is stored in the digital library. By adding this, we can generate a complete GDS2 file that includes all the components and their actual layout structure. The GDS2 file is a critical output of the design process, as it is used for manufacturing the chip. This GDS2 file also needs to undergo checks, specifically DRC and LVS checks, which we will discuss later. For now, just know that these checks are crucial to ensure that our layout meets the design rule specifications and that the connections of the components in the layout accurately reflect the logic synthesis and gate-level netlist we generated earlier. DRC checks ensure that the design adheres to the physical constraints of the manufacturing process, while LVS checks verify that the layout matches the intended logic design. If everything passes, it confirms that our layout is manufacturable and that the connections align with our original logic design. This means the layout accurately represents our initial ideas, allowing us to generate the final GDS2 file, which can then be submitted to the foundry for the next steps. The successful completion of these checks is a testament to the accuracy and reliability of the design process, ensuring that the final product will function as intended. So, throughout this entire process, logic synthesis, layout, routing, and all these actual checks will have dedicated EDA tools to assist designers in completing this process. Therefore, the automation level of digital circuit layouts is actually very high. The automation level is indeed very high, meaning that the software support is quite powerful. With EDA tools, generate layout files from Verilog code, a feature of digital integrated circuit layout design. Explore analog integrated circuit layout design, differing due to lower automation. Mainly hand-drawn, start with circuit design using basic components like transistors, resistors, capacitors, and inductors. Simulate to ensure functionality matches your concept. Simulations occur in frequency and time domains. As real circuits operate in real time, observing signal waveform changes. Hand-drawn process. Start with an idea, then circuit design. Use basic components like transistors, resistors, capacitors, inductors. Ensure input-output matches the idea. Simulate to verify. Include frequency and time domains for real-time operation. Observe waveform changes. Perform time domain simulation. Check if simulation aligns with specs. Modify if needed. If correct, proceed to layout. Layout involves manual drawing. Consider matching, noise, as poor layout affects characteristics. After layout, perform DRC and LVS checks. DRC ensures design rules. LVS checks layout. This connection forms a circuit structure, aligning its function with your design idea. This is circuit design. After designing, simulate to check if the circuit matches your idea. Simulations occur in frequency and time domains, as circuits operate in real time, showing waveform changes. Time domain simulation is crucial. Verify if simulation results match design specs, including constraints. If not, modify your design. If they do, proceed to layout. Layout follows design but involves manual drawing of components with high effort and low automation. Consider factors like matching and noise, crucial for circuit characteristics. After layout, perform DRC and LVS checks. DRC ensures layout meets rules, and LVS checks if connections match the design netlist. Incorrect connections cause LVS failure. Pass these checks to proceed. If not, modify your design. These are physical verification checks. After passing, extract parasitic parameters, mapping them back to the schematic. The netlist, post-schematic, is used in LVS and post-simulation, incorporating parasitics to form a post-layout netlist. Perform post-simulation. If it passes, the circuit is reliable. If not, check layout issues or design margins. Modify layout or design if needed. Failures often indicate poor layout. If post-simulation passes and meets parameters, generate the final GDSII file for tapeout. This is the analog circuit design process. So, we need to perform a time domain simulation to see actual signal waveforms. Here, we check if the simulation results align with your design specifications, i.e., design constraints and parameters. If they don't match, you must modify your design. If they do match, proceed to layout. In the flowchart, layout directly follows circuit design. In reality, layout involves manually drawing each component layer by layer. Thus, manual work is high, automation low. Also, consider more factors than digital circuits like matching, noise, etc., as poor layout affects circuit characteristics. Now, see how this affects the process. After layout, perform DRC and LVS checks. DRC checks if layout meets design rules, i.e., geometric shapes conform to processing requirements. LVS checks if component connections in layout match netlist from initial design. If connections have issues, LVS fails. Only after passing these checks can you proceed. If not, modify your design. These checks are physical verification. After passing, perform parasitic extraction. This involves extracting parasitic info from layout to schematic. After initial schematic, a netlist is generated. This netlist is for LVS and post-simulation, incorporating parasitic parameters. Then netlist generates a post-layout netlist reflecting parasitic info. Then perform post-simulation. If post-simulation passes, circuit is reliable. If it fails, check layout issues. If layout is problematic, modify it. Initial design may have issues, i.e., insufficient margins. Even with optimized layout, it may not meet specs if margins are insufficient. In this case, modify circuit design. If post-simulation fails, modify layout or design. Usually failure is due to poor layout. If post-simulation passes and meets design parameters, generate final GDSII for tapeout. This is analog IC design process. The connection relationships of the components in the layout must be consistent with the netlist generated from our initial circuit design, right? If the connections are problematic and do not reflect the original circuit design, then LVS will fail. Only after passing these two checks can you proceed to the next step. If you don't pass, you need to continue modifying your design. These two checks combined are called physical verification. After passing physical verification, you need to perform parasitic parameter extraction. This step involves extracting parasitic information from the layout and mapping it back to your original schematic. So, you can see that after completing the initial schematic design, a netlist is generated. This netlist needs to be provided for the LVS step and also for the post-simulation step, where it will incorporate the parasitic parameters into the netlist. At this point, the netlist generates a post-layout netlist that reflects the parasitic information from the layout. Then, you perform post-simulation. If the post-simulation passes, then your circuit is considered reliable. If the post-simulation reveals that it does not meet your original design specifications, you need to check if the layout has issues. If the layout is problematic, you need to modify it. It's also possible that your initial design had issues, meaning your design margins were insufficient. Even if you optimize the layout, it may not meet the required specifications if the circuit margins are not enough. In this case, you might need to go back and modify your circuit design. So if the post-simulation fails, it could mean you need to modify the layout or your original design. However, in most cases, the failure is due to poor layout design. If the post-simulation passes and the results meet your initial design parameters, then you can generate the final GDSII file for tapeout. This is the process of the analog integrated circuit design. Now let's take a look at the specific requirements we have when designing layouts in detail and thoroughly. Here we are particularly focused on analog circuits, as this video tutorial emphasizes analog integrated circuits specifically. So, what do we need when designing layouts for analog circuits? First of all, it is important to note that we must focus on the IC process knowledge needed for layout design. Understanding IC manufacturing helps relate drawn layers to substrate layers. Secondly, besides IC processing, basic circuit design knowledge is needed. It aids layout creation. Thirdly, analog layout design demands patience and personal style. Patience is key due to precision in analog circuits, considering matching and parasitics. Style involves personal habits like matching methods. Layout is about planning. Layout involves multi-layer drawing and planning. This is crucial because you need a clear plan from the start. So the second point is that you need to grasp IC processing and basic circuit design knowledge. Even if you are not designing the circuit, understanding circuit design helps in better layout creation. The third point is that designing analog layouts requires patience and personal style. These two aspects are essential for analog circuits. You need patience because the level of hand drawing is high for analog circuits. You must consider factors like matching and parasitics, which are time-consuming. Style refers to personal habits, like preferred matching methods or component isolation. An important point is that layout is not just drawing, it's planning. Initially, we mentioned layout involves multi-layer drawing. Layout seems like creating shapes, but it's more about planning ahead. Why? Because when drawing the layout, you should have a clear idea from the start of what to create. Think about what to draw and the overall layout. Before drawing, have a complete concept of the layout in mind, including the general layout. So, when we talk about style, it actually refers to your personal habits. There are some habits to it. Layout is not just drawing, but planning. Layout involves multi-layer drawing. Yes, multi-layer drawing means creating graphics with multiple layers. Layout is not just drawing shapes, it's about planning. This is because when you're drawing the layout, you need to have a clear idea of what you want to create. Think about what you're going to draw and the overall layout. Before drawing, have a complete concept of the layout. Consider which components need to be matched and which need to be isolated. This requires a plan. You can't just draw as you go. Otherwise, creating a good layout is difficult. Plan ahead how to draw it. At the start, sketch rough drafts before the actual layout. When designing, adopt an analog mindset, thinking in terms of analog circuits and adhering to design principles. An analog mindset involves considering matching, timing, and other aspects. Keep these in mind as they are crucial when designing. Before drawing, think about what you will create. Have a clear idea of the layout. Plan the layout in your mind, considering which components match or need isolation. Preliminary planning is essential. Drawing without a plan makes it hard to achieve a good layout. Start with a clear plan. Sketch rough drafts on paper before drawing the layout. When designing an analog layout, adopt an analog mindset. This involves thinking in terms of analog circuits and adhering to analog design principles. We will discuss the analog mindset later, focusing on matching, timing, and other key aspects. Keep these principles in mind as they are crucial for designing analog circuit layouts. You need to plan ahead about which components need to be matched and which need to be isolated. This preliminary planning is crucial. You can't just draw as you go along. If you do that, it will be very difficult to create a good layout. You need to have a clear plan in place from the beginning about how you are going to draw it. So, before you start drawing the layout, you might want to sketch some rough drafts on a piece of paper before moving on to the actual layout drawing. Lastly, when designing this analog layout, you must adopt an analog mindset. This means you need to think in terms of analog circuits and strictly adhere to the principles of analog circuit design. What does an analog mindset entail? We will discuss this later, but it involves considering factors like matching, timing, and other important aspects. You need to keep these things in mind at all times, as they are crucial principles to follow when designing analog circuit layouts. It's essential to always think about these aspects, as they are fundamental to the design of analog circuits. Let's introduce two parameters for transistors, finger and multiplayer. Finger divides the gate into segments, alternating source and drain. Multiplayer duplicates the transistor. Width and length are W and L. For a finger, WL is the width to length ratio, same for multiplayer. In circuit design, both parameters are used. If finger equals 3 and multiplayer equals 2, the total WL is the single finger's WL times the number of fingers and multipliers. Wider transistors are divided into fingers or modules, which we'll discuss later. The first one is called finger, which means dividing the gate of a morphite. When we draw a morphite, we take its gate, let's say this is its gate, and we cut it into several segments, just like fingers. So we have segments alternating between the source and drain. For example, this is the source and this is the drain. By doing this, we can create a very wide transistor divided into segments. If we say finger equals 3, then we can see that there are 3 segments. What are the benefits of this? We'll discuss that later, but for now, just know that this is called finger. The next one is called multiplayer, which means multiplying or duplicating. It refers to directly copying the same transistor. For example, if multiplayer equals 2, that means we have 2 copies of the same transistor. So you see this transistor has its source, drain, and gate, and this one also has its source, drain, and gate. These 2 transistors are identical copies. Now let's look at the width and length of the transistor. For a finger, its width is in this direction, which we call W, and its length is in this direction, which we call L. So for one finger, the width to length ratio is WL. The same goes for multiplayer. It also has its WL. When we design a schematic for a circuit, both finger and multiplayer parameters will appear. If I input finger equals 3 and multiplayer equals 2, then what is the actual width to length ratio of the transistor? We calculate the total width to length ratio as follows. The total WL is the single finger's WL multiplied by the number of fingers and then multiplied by the number of multipliers. For example, if multiplayer equals 3, that means we have 3 fingers, right? So we have 3 segments. Each segment has a width to length ratio of WL. Since these 3 segments are connected in parallel, we connect the sources together and the drains together, so in the end these 3 fingers are in a parallel configuration. Thus, for a transistor with finger equals 3, its width to length ratio is WL multiplied by 3. If I then add another multiplier equal to 2, that means I need to copy this entire setup again and connect the corresponding ports in parallel. So, in total, we multiply by 2 again. This results in a total width to length ratio of 6 times WL. So now, the total width to length ratio is 6 times WL. This is how we calculate the total width to length ratio. When we design wider transistors, we usually break them down into several fingers or modules. As for why we do this, we will discuss that later. So, if multiplayer equals 3, what does that mean? It means we have 3 fingers, right? That means there are 3 channels, and each channel has a width to length ratio of WL. Since we have 3 channels, they are connected in parallel. Why? Because the source and drain alternate, and in the end, we connect the sources together and the drains together. So essentially, these 3 fingers are set up in a parallel configuration. Therefore, for a transistor with finger equals 3, its width to length ratio is WL multiplied by 3. Now, if I add another multiplier equal to 2 on top of that, what does it mean? It means I need to copy this entire setup again, right? So I copy it and connect the corresponding ports in parallel. This means we multiply by 2 again, resulting in a total width to length ratio of 6 times WL. So now, the total width to length ratio is 6 times WL. This is how we calculate the total width to length ratio. When we design wider transistors, we usually break them down into several fingers or modules. As for why we do this, we will discuss that later. Next, I want to introduce the cross-section of the IC to show its 3-dimensional structure. The IC layout is a multi-layer process, and these layers form the chip's 3D structure. Let's examine the cross-section to understand this. This is a 180 nanometer CMOS process, EP4M technology. P stands for polysilicon and M for metal, indicating 1 polysilicon and 4 metal layers. The cross-section shows the silicon substrate or active area connecting to M1 metal 1 via a contact CT. There are 4 metal layers, M1, M2, M3, and M4, topmost, or MT. Insulating layers of silicon dioxide separate these metal layers, preventing electrical connections. To connect M1 to M4, we use vias like VL1 for M1 to M2, The P is an abbreviation for polysilicon, and M is an abbreviation for metal, right? So EP4M means 1 polysilicon and 4 metals, which indicates that this process provides 1 layer of polysilicon and 4 layers of metal. Essentially, it represents a type of interconnect in this process, 1 poly and 4 metals. Now looking at the cross-section of this process, it looks like this. On the left side, we see the cross-section. The bottom part here is actually our silicon substrate, or what we call the active area. The active area connects through something called a contact, which we usually abbreviate as CT. This contact connects the active area to M1, which is the abbreviation for metal 1, the first layer of metal. Since there are 4 metal layers in this process, we also have M2, M3, and M4. M4 is the topmost metal layer, right? So the topmost metal is usually abbreviated as MT, meaning top. So M4 is our M4. Now the metals have different layers, so they are separated in 3-dimensional space. Between the metal layers, there are insulating layers of different colors, which are actually insulating layers made of silicon dioxide. So between the metal layers, there is an insulating medium that isolates them. Even though it looks like they are all stacked together when viewed from above, there is actually no electrical connection between them because they are isolated by insulating media. If I want to connect M1 to M4, how do I do that? I need to use something called a via or VL. There are several types of vias. For example, the via connecting M1 to M2 is called VL1, and the one connecting M2 to M3 is V1. The metals have different layers, so they are separated in 3-dimensional space. Between the metals, there are insulating layers of different colors, which are actually insulating layers made of silicon dioxide. So the metals are isolated from each other by this insulating medium. Even though it may look like they are all stacked together when viewed from above, there is actually no electrical connection between them because they are separated by insulating materials. If I want to connect M1 to M4, how do I do that? I need to use something called a via, or VL. There are several types of vias. For example, the via connecting M1 to M2 is called VL1, and the one connecting M2 to M3 is V1. Connecting 3 to 4 is VS3, allowing interconnection of metal layers through vias. This is the chip's layout structure. Now let's examine the thickness. The total thickness from metal 1 to 4 is about 5 microns. The metal thickness is about 0.5 meter. Why emphasize this? To highlight that layouts are viewed top-down, but ignoring the 3D structure can cause issues. When drawing layouts, remember they have a 3D structure once processed. For example, drawing two metal lines. The blue is the substrate, and on it we draw two gray M1 lines. From above, we see two M1 lines. However, the actual structure has thickness. For this process, it's 0.5 microns. The metal's thickness is about 0.5 millitorr. Why emphasize this? It's crucial to remember that layouts are viewed top-down, but they have a three-dimensional structure. Ignoring this can cause issues. When drawing layouts, keep in mind the 3D structure. For example, two metal lines on a substrate appear as two M1 lines from above. However, processed, they have thickness. In this process, it's 0.5 microns, which is thick. In a 180 nanometer process, a metal line can be 180 nanometers wide, defined by the transistor's minimum gate length. The metal line's width is usually wider, like 220 nanometers, which seems thin but is 500 nanometers thick. After processing, these lines resemble walls with parasitic capacitance between them due to thickness. Metal lines are separated by insulating materials, forming a capacitor. The capacitance size relates to the metal plate's area. The 0.5 micron thickness is significant, and long distances increase parasitic capacitance, affecting signals. We'll explain estimating this impact later. For now, understand that parasitic capacitance exists. When we draw the layout, we view it from above, seeing the two M1 lines. However, once processed, the structure shows M1 with a thickness of 0.5 microns. This is quite thick compared to a 180 nanometer process where metal lines are typically 180 nanometers wide, defined by the minimum gate length of transistors. After processing, the M1 line resembles a wall with parasitic capacitance existing between these walls due to the metal's thickness. Insulating materials separate the metals, forming a capacitor. The 0.5 micron thickness is significant, and long distances increase parasitic capacitance, affecting signals. We'll explain how to estimate this impact later, but for now, understand that parasitic capacitance exists. The 0.5 microns is actually quite thick. When we use a 180 nanometer process to draw a metal line, this line can typically be drawn to a width of 180 nanometers. The 180 nanometers represents its feature size, which is often defined by the minimum gate length of the transistors. For example, in a 180 nanometer process, the minimum gate length of my transistor is 180 nanometers. This also limits the width of our metal lines, but the width of the metal lines is generally a bit wider than that. Let's say we draw a metal line with a width of 220 nanometers, and this 220 nanometers looks quite thin, right? But in reality, you have to consider its thickness as well. It has a thickness of 500 nanometers. So when you draw this small M1 line on the layout, what you actually get after processing is like a wall. So these two M1 lines are like two walls, and between these two walls, there exists parasitic capacitance. This diagram is mainly to give everyone an intuitive understanding that there is parasitic capacitance between metal lines. This is because the metal has a certain thickness, and the side walls of the metal will form parasitic capacitance. The metal and metal are separated by insulating materials. For example, there is insulating material in between, and this is one metal, and this is another metal. What is this? This is essentially a capacitor with two metal plates separated by some insulating material. The size of the capacitance is related to the area of the metal plates. So you can see that the metal has a certain thickness of 0.5 microns, which is quite thick. If the distance is long, the parasitic capacitance between the two metals cannot be ignored, and it will affect your signal. We will have specific explanations on how to estimate this impact later. For now, just have an intuitive understanding that this parasitic capacitance exists.
So the next point is that, as we have previously discussed as mentioned earlier, when we design layouts, it's important, crucial, and essential for everyone to understand some basic knowledge to have a comprehensive and thorough understanding of the entire and complete process flow, right? This fundamental and basic understanding helps us to better comprehend and understand the corresponding and related masks for these specific layouts and the various roles and functions of those masks. Therefore, let us briefly and concisely review the CMOS process flow in detail. However, many of the processes here have been simplified and condensed, focusing only on some very key and critical nodes for our introduction and explanation. First, let us look at the very first step, which is commonly referred to as the growth of field oxide, often abbreviated and written as FOX. In our current and modern CMOS process, it is typically processed and carried out on a P-type substrate. This means that the substrate is indeed P-type. On this P-type substrate, we first grow and develop the field oxide. What is the purpose and function of this field oxide? Its main and primary role is to provide isolation and separation for the devices. In other words, when we process and manufacture multiple MOSFETs on the same and identical silicon substrate, we need to create and establish electrical isolation between these MOSFETs, and that is where the field oxide comes in, as it is an insulator and isolator. Of course, this field oxide process is usually and typically used for processes above the 0.35 micron node. For processes below 0.35 microns, which is currently the deep sub-micron process, we use STI isolation instead of field oxide. STI stands for shallow trench isolation. Essentially, this involves digging and excavating a trench in the areas where there is no oxide, filling that trench with oxide, and then using chemical-mechanical polishing to flatten and level the surface. Regardless, in the process of growing and developing the field oxide and then removing it, we utilize the active layer, which is the active region, while everything outside of that is either field oxide or STI. In our example, we are using field oxide as a reference and example. Then we first need to remove some field oxide. After removing part of it, we aim to do N-well implantation by injecting the N-well here. After that, another portion of field oxide needs removal for forming NMOS within which PMOS forms. I've removed field oxide in these areas corresponding to active regions. For STI, areas with field oxide are isolated by STI before growing gate oxide for MOSFET gates, followed by polysilicon layer etching using photolithography, requiring a polishing plate. Next comes ion implantation, forming NMOS at this position, while P-type implants form PMOS within an N-well, leading us towards interconnections creation through nitride growth, then hole etching followed up metal deposition and its subsequent etch creating interconnect lines, SIMP. Lifting process flow further. Let's examine three-dimensional chip processing structure illustrating CMOS process flows, defining mask roles during integrated circuit processing, introducing concepts like clear tone and duct tone explained next. During IC processes, multiple masks, layers used defined via layouts. What structures make these? This diagram shows one such mask composed mainly from two parts, metal, chrome. We etch polysilicon to form the gate using photolithography, needing a polishing plate. Ion implantation forms NMOS and PMOS. With both formed, we create interconnections by growing nitride, etching holes, depositing and etching metal. This is a simplified process. Next, a 3D diagram shows the CMOS process and mask. Now that both NMOS and PMOS have been formed, what do we do next? We create interconnections, right? First, we need to grow some nitride, then etch holes, followed by metal deposition, and then perform metal etching. This way, we can create the interconnect lines. This is a simplified process flow. Next, let's look at a three-dimensional structural diagram of chip processing to illustrate the entire CMOS process flow and how the layouts we design define our masks, as well as the roles these masks play in the integrated circuit processing. Before that, we need to introduce two concepts. One is called clear tone, and the other is called duct tone. What do these two concepts mean? Let's take a look. First of all, during the integrated circuit processing, we will definitely use many layers of masks, right? As we mentioned earlier, the patterns on these masks are defined by our layouts. So, what kind of structure is this mask? In fact, in this diagram, this object is a mask. Its composition mainly consists of two parts. One part is a metal chrome, which is called metal chrome. This type of metal is definitely opaque, right? It's not transparent. And then we have another layer, which is glass, a type of glass that is transparent. So the overall structure of the mask consists of metal deposited on this transparent glass substrate. On the metal layer, we have various patterns, and these patterns are defined by our layout. In this case, the patterns on the metal layer can be divided into two types. The first type, like the one on the left, is characterized by most of the mask being covered with metal, with only a small portion of the pattern being etched away, creating a hollow space. For example, if we have the letters X, Y, Z, it means that when we draw our layout, we have created these three shapes. For this polishing plate, the positions of the letters X, Y, Z are hollow, meaning there is no metal there, while the other areas are covered with metal. So, we call this type of polishing plate a dark field. The clear tone mask, or dark field mask, is completely opaque, with only a small number of hollow patterns that allow light to pass through. For this type of mask processing, we refer to the layer of the mask as clear tone. Since these positions are hollow, if I shine light from above the mask, the light can pass through these hollow areas, right? Below, the red area represents the photoresist, which is placed on the wafer. This means that only the hollow positions can receive light exposure, allowing for the corresponding changes to occur in the photoresist. Typically, in integrated circuit processing, we use what's called positive photoresist. Positive photoresist means that the areas exposed to light will undergo a change, and we can wash away the areas that were exposed using our developer solution, while the areas that weren't exposed will harden, thus preserving those areas. So through this process, we can see that this is called clear tone. Clear tone essentially means that the patterns defined in the layout are transparent, so the layers with the clear tone property define the hollow positions in the mask. This means that during the processing, the corresponding photoresist patterns will be removed. So clear tone means that the patterns are removed, meaning that the patterns defined in your layout will be removed from the photoresist. Now the counterpart to this is called dark tone. So what does dark tone look like? Let's say we have three patterns, X, Y, and Z, drawn in the layout. If this layer has the dark tone property, what does it look like? The mask would look like this. This type of mask can also be called a bright field mask. A bright field mask means that most of the mask has no metal barriers, and only the locations with patterns have metal barriers, which can block the light. So we can see that we defined the positions of patterns X, Y, and Z, and only those positions have metal barriers to block the light. The other areas allow light to pass through. Therefore, if we use this type of mask for photolithography, we can imagine what will happen to the photoresist below. The photoresist at positions X, Y, and Z will not be exposed to light, while the other positions will be. Since we are using positive photoresist, the areas that receive light exposure can be washed away. After photolithography, the pattern in the photoresist will become X, Y, and Z, so you can see that the patterns X, Y, and Z are preserved. Thus, when we refer to dark tone, it actually means that the patterns are preserved. So when we draw the layout, there are two properties. One is clear tone, and the other is dark tone. Of course, when we are drawing the layout, we don't deliberately focus on whether this layer is clear tone or dark tone. This will be relevant during the processing stage. However, designers need to be clear about whether this layer is clear tone or dark tone, as it determines whether the patterns in the photoresist will be etched away or preserved during photolithography. If we want to etch away the patterns we drew, we need to use clear tone, meaning that the drawn patterns need to be transparent. If we want to preserve the patterns we drew on the photoresist, we will use dark tone, which is opaque. So opaque patterns will be preserved. This is the concept. Now that we've introduced this concept, let's look at the entire processing flow. First, let's take a look at the first step. What example should we use? Let's use the example of processing a bright field mask means that most of the mask has no metal barriers, right? Only the areas with patterns have metal barriers, so we can see that we define the positions of patterns X, Y, and Z, and only those positions have metal barriers to block the light. The other areas allow light to pass through. So if we use this type of mask for photolithography, we can imagine what will happen to the photoresist below. The photoresist at positions X, Y, and Z will not be exposed to light, while the other positions will be. Since we are using positive photoresist, the areas that receive light exposure can be washed away. After photolithography, the pattern in the photoresist will become X, Y, and Z. So you can see that the patterns X, Y, and Z are preserved. This is why we call it dark tone. It actually means that the patterns are preserved. So when we draw the layout, there are two properties. One is clear tone, and the other is dark tone. Of course, when we are drawing the layout, we don't deliberately focus on whether this layer is clear tone or dark tone. This will be relevant during the processing stage. However, designers need to be clear about whether this layer is clear tone or dark tone, as it determines whether the patterns in the photoresist will be etched away or preserved during photolithography. If we want to etch away the patterns we drew, we need to use clear tone, meaning that the drawn patterns need to be transparent. If we want to preserve the patterns we drew on the photoresist, we will use dark tone, which is opaque, or opaque patterns will be preserved. This is the concept. Now that we've introduced this concept, let's look at the entire processing flow. First, let's take a look at the first step. What example should we use? Let's use the example of processing Let's take a PMOS transistor as an example to look at the entire processing flow. First of all, to process a PMOS, it must be done on an N-type substrate, right? Most of the integrated circuits we use today are on P-type substrates. So we need to process a PMOS on a P-type substrate, which means we need to create an N-well first. So the first step is to perform photolithography for the N-well. At this point, we will use the first mask, which is our first layer, the N-well. We draw a rectangle for the N-well. Now, what is the property of this N-well? We mark it as clear tone, and we use the abbreviation C to indicate that it is cleared. So, if it is cleared, what does our mask look like? It looks like this deep green one, which is our N-well mask. You can see that it is clear tone, meaning the areas with patterns are transparent, while the areas without patterns are blocked by metal chromium, right? Now, let's take a cross-section along line AA to see what it looks like. The whole thing looks like this. First, there is a P-type silicon substrate at the bottom, and on top of that, there will be a layer of silicon dioxide acting as a protective layer. Then we spin coat photoresist on top of that. Note that we are using positive photoresist, right? We use the N-well mask to perform photolithography. Since it is clear tone, the areas exposed to light will be removed. So the areas that are exposed to light are roughly in this position, right? These areas will be cleared away. After processing, it looks like this. The photoresist layer has been opened up. After opening it, we can proceed to the next step, which is the oxide etching, where we etch away the silicon dioxide on the surface of the silicon, exposing the silicon underneath. Next, we perform the N-well implantation. Note that this step does not require an additional photomask because the implantation is done over the entire wafer. Here you can see the role of silicon dioxide. It acts as a protective layer, allowing the N-well implantation to occur only at the openings in the silicon dioxide, while other areas are shielded by it. So where are the openings in the silicon dioxide? That would be our N-well, right? So you can see why we use clear tone. Clear tone is used to clear certain patterns. Generally, in our processing techniques, if we are making holes or openings, we usually use clear tone. If we want to keep something, we typically use dark tone. After performing the N-type ion implantation, we will form an N-well. You can see that the edge of this N-well actually extends into the silicon dioxide layer a bit. This is mainly because after implanting the N-well, we need to perform an annealing step. During annealing, the implanted ions will undergo thermal diffusion, spreading out into the surrounding area. After diffusion, the actual area of the N-well formed will definitely be larger than the implantation area, so it extends into the silicon dioxide below. Now at this point, our N-well processing is considered complete. The next step is to define our active area. Before that, we first need to remove all the silicon dioxide on top and then grow a new layer of silicon dioxide because the previous layer has been damaged due to ion implantation and the patterns have been destroyed. So after growing a new layer of silicon dioxide, we will deposit a layer of lightly doped silicon on top, and then we will select photoresist again. Next, we will perform photolithography for the active area. For the active area photolithography, we need an active layer, right? This corresponds to a mask. Let's take a look at how we draw this layer. It looks something like this with two shapes, a rectangle and a square. These two areas represent our active region, which will be used to form our channel region, right? This part is used to form our substrate contact. This part is specifically used to essentially form our substrate contact in order to effectively and efficiently create a connection. Region properties and layers. Photolithography retains the pattern. Dark tone areas have metal chromium. Non-patterned areas are hollowed. Light exposure retains patterns. Silicon nitride and dioxide are etched.
Photoresist preserves the pattern. Dark ton preserves patterns. Field oxide grows for isolation. Outside silicon nitride, oxide thickens. Remove oxide inside active region. Second layer, active. Grow thin gate oxide for ridges. Thin silicon dioxide layer is grown. No polishing plate needed, wafer covered. The parts without patterns are empty, so when exposed to light, the resist in the pattern parts is retained, the rest is washed away. Next, we etch Si3 and 4 with SiO2. As this is protected by resist, the pattern here is preserved. This is the role of dark ton, to preserve patterns. This way we keep the active pattern here. What comes next? We grow the field ox for isolation. As this has Si3 and 4 protection, only outside parts grow a thicker ox. After this growth, we remove the ox inside the active region. After ox growth, we end up with this form. At this point, we used a second LVL, the active LVL. Next, we grow the thin gate ox to form ridges. The ox needs to be thin, so we grow a very thin SiO2 layer across the surface, the thin gate ox. This step doesn't need a polishing plate, and there's no corresponding LVL as the wafer surface is covered with thin gate ox. Next, we form our gate. Before that, we deposit poly first, called poly deposition. This step doesn't need a polishing plate. It covers the area with poly. After that, we remove the poly outside the gate to keep the gate form intact. To retain the gate, we use a pattern, and this LVL's property must be dark. We use a new LVL called the poly layer to define the MOS core ridge. We overlap a strip above the main active region of the dev, forming the core form of our MOS core dev. The property of this LVL is dark, so the parts with patterns have metal, while the parts without patterns are empty. When exposed to light, the resist in the parts without patterns is removed, while the resist protected by the mask is retained. What comes next is the etching of poly etching. As there's resist protection above the gate, this poly area isn't etched away, while the poly in other parts is completely etched away. This area has resist. We grow a thin gate oxide layer, applying silicon dioxide. To form the gate, we deposit polysilicon and remove excess to maintain the structure. A poly layer defines the MOS core ridge. Next is polysilicon etching. The gate's polysilicon, protected by photoresist, remains intact, while other areas are etched away. Next, we need to form our gate, right? But before that, we definitely need to deposit polysilicon first, which is called polysilicon deposition. This step also doesn't require a polishing plate. It covers the entire area with polysilicon. After that, we need to remove the polysilicon outside of the gate to keep the gate structure intact, right? Clearly, to retain the gate, we need to use a pattern, and the property of this layer must be dark, right? So at this point, we will use a new layer called the poly layer to define the MOS core ridge. We overlap a long strip above the main active region of the device, forming the core structure of our MOS core device. The property of this layer is dark, so you can see that the areas with patterns have metal, while the areas without patterns are hollowed out. When we expose it to light, the photoresist in the areas without patterns is removed, while the photoresist protected by the mask is retained, right? So what comes next is the etching of polysilicon etching. Because there is photoresist protection above the gate, this area of polysilicon is not etched away, while the polysilicon in the other areas is completely etched away. Just to clarify, this area actually has photoresist, and there is a bit of an issue with this diagram. This area also has photoresist. When it comes to photoresist, it forms a shape that, if you were to make a cross section from this side, would look like this. This shape has photoresist at the bend as well, so after we go through the polysilicon process, the polysilicon pattern grows like this. From this image, you can also see that the layers we previously discussed, the layout of these layers, are all double images, but they actually reflect a three-dimensional structure of our integrated circuit, right? So you can see this is the gate we designed, and this is the actual processed gate. You can see the correspondence between them, right? The shapes we draw are essentially projections on this surface, right? The real structure has a bend at this position, right? It has a three-dimensional structure, and this bend is not visible in the layout, right? You can only see it after processing. So when you're drawing, you need to have this three-dimensional structure in your mind. Now, up to this point, our gate has been processed. Next, we need to form our substrate contact and the source drain region, right? So first, we will perform the spin coating of photoresist.
then we need to form the substrate contact. So we will perform N-type implantation at this substrate contact position. We need to expose the N well, which is definitely an N-type implantation. The yellow dashed box indicates our N implant. For N well implantation, you need to open a specific area, and at that opening we perform ion implantation, right? So its property must be clear, and you can see it has a clear tone property. For our photoresist layer, we can see that the area where we draw the pattern is hollow, right? This area is hollow, while the areas without patterns are covered with metal chrome, which are not hollow. So when we expose it to light, only the hollow areas can allow the light to shine through. This means that only in the hollow areas can the photoresist be washed away, right? This way, we form an opening. After forming the opening, we proceed with the N-type ion implantation. Since only this area has an opening, only this area can receive the implanted ions, while the remaining areas are blocked by the photoresist. So, in this position, an N-type region is formed, which is the contact for the N well, right? This is the N-type implantation. After the N-type implantation is completed, it looks like this. Next, we need to form the source drain region, which means we need to perform P-type implantation in the main area of this device. We are drawing a P-cap, so we need to do a P-type implantation. The green dashed box indicates our P-type implantation. Clearly, it should have the same properties as the N-type implantation. It also needs to be opened and then undergo particle implantation, so its property is also clear tone. For our photoresist layer, the areas with patterns are hollow, while the areas without patterns are covered. So only the areas with patterns can have the photoresist etched away, right? After etching, we perform ion implantation, and only the areas where the photoresist has been etched away can receive the ions, while the remaining areas cannot. Alright, at this point, our P-type implantation is complete. The source, drain region, substrate, and polysilicon have all been formed, right? Next, we need to proceed with the interconnection. The first step in the interconnection is to connect our source and drain, substrate, and polysilicon to M1 using contacts. So we first need to process the contacts. For that, we need to grow silicon dioxide on the surface for insulation. After growing the silicon dioxide, we need to etch out the holes for the contact processing. You can imagine that to etch holes, we need to remove the pattern, right? So we use something called clear tone to do that. After we spin coat the photoresist, we use a contact mask, which is also clear, meaning the areas with patterns are hollow. This way, when we expose it to light, the photoresist in the hollow areas can be washed away. Then we proceed to do the zinc oxide etching, which is etching the thick silicon dioxide we just grew. This way, we can etch small holes in those areas, right? We keep etching until we reach our source or drain region, substrate contact, and polysilicon. After that, we perform tungsten deposition, which is a metal deposition process. This allows us to form metal contacts in the areas where we just etched some holes. These contacts are small pillars made of metal that connect our substrate, source, drain, and gate together. Next, we need to connect them to our M1, right? So we will process M1. First, we need to deposit metal on M1, so M1 will be connected to our metal. Then, we need to keep our interconnect lines intact. After that, we will spin coat photoresist on M1 and etch it. The etching process means we need to keep the patterns we want, which are the necessary metal interconnect lines, while removing the unnecessary ones. So during the photolithography process, we need to retain some of the interconnect line patterns. For this, we use a backtone. The metal polishing plate will have metal in the areas where there are metal lines blocking the light, while the areas without patterns will be transparent. This way, when we expose it to light. Zinc oxide etching is the process where we take the relatively thick silicon dioxide we just grew and etch it. This way, we can create small holes in these positions, right? We keep etching until we reach our source drain region, substrate contact, and polysilicon. After that, we perform tungsten position, which is a metal deposition process. This allows us to form metal contacts in the areas where we just etched some holes. These contacts are small pillars made of metal that connect our substrate, source, drain, and gate together. Next, we need to connect them to our M1, right? So we will process M1. Now first, we need to connect M1 to our metal. This way, M1 will be linked to our metal, right? Then we need to keep our interconnect lines intact. After that, we will spin coat photoresist on M1 and etch it. The etching process means we need to retain the patterns we want, which are the necessary metal interconnect lines, while removing the unnecessary ones. So during the photolithography process, we need to preserve some of the interconnect line patterns. For this, we use a backtone. The metal polishing plate will have metal in the areas where there are metal lines blocking the light, while the areas without patterns will be transparent. This way, when we expose it to light, only the areas where we have drawn the metal lines will have their photoresist retained, while the rest will be removed. This way, when we etch the metal, the photoresist protects the metal patterns, allowing us to keep them intact. So, up to this point, we have completed the metal connections for the source, drain, substrate, and polysilicon. First, we need to connect M1 to our metal, so M1 will be linked to our metal, right? Then we need to preserve our interconnect lines. After that, we will spin coat photoresist on M1 and etch it. The etching process means we need to keep the patterns we want, which are the necessary metal interconnect lines, while removing the unnecessary ones. So during the photolithography process, we need to retain some of the interconnect line patterns. For this, we use a backtone. The metal polishing plate will have metal in the areas where there are metal lines blocking the light, while the areas without patterns will be transparent. This way, when we expose it to light, only the areas where we have drawn the metal lines will have their photoresist retained, while the rest will be removed. This way, when we etch the metal, the photoresist protects the metal patterns, allowing us to keep them intact. So, up to this point, we have completed the metal connections for the source, drain, substrate, and polysilicon. So, only the areas where we drew the metal lines are going to have their photoresist retained, while the rest will be removed. In the process this way, when we etch the metal, the photoresist essentially protects these metal patterns, allowing them to be preserved, right? So up to this point, in this manner, we have completed the metal connections for the source, drain, substrate, and polysilicon. So the next part is about processing the insulation layer on the motor and making holes, vias. We then process higher level metals, and this continues until we complete the entire interconnect structure. Once done, it looks like this. This is a multi-layer metal interconnect. Using 4 metal layers, the bottom is 1M1, top is 4M4. The highest metal layer is MTT, or top metal. To connect M1 to M2, we use vias due to insulating media. Insulating media between layers prevents electrical connection. To connect metal levels, we use vias. To connect M1 to M2, M2 to M3, and M3 to M4, we need vias. This completes the interconnect structure. We remove oxide from the wire section to clarify the structure. Hiding this oxide part reveals the internal structure. Metal connects through this contact to the body and drain region. Showing the oxide completely, it looks like this. The oxide, like glass, is somewhat transparent. This is our interconnect, with oxide between them. The oxide extends all the way up here. To show the metal structure, we hid the oxide above. Using this 3D structure, we demonstrated PMOS transistor processing and layout usage. Now, let's look at an NMOS transistor. We discussed PMOS, but we use NMOS technology now. NMOS technology includes both NMOS and PMOS. NMOS processes directly on the P well. PMOS must be processed in an N well. Let's look at the circuit layout and chip floor plan. This is our schematic diagram, or schematic. The schematic looks like this. For example, this is an inverter design. This is an inverter circuit. Of course, we removed this just to clearly show the internal structure, so we hid the oxide in this area. Now we can see that the structure inside looks like this. The metal connects through this contact, meaning metal 1 connects through the contact to our body contact and drain region, like this. If we display the oxide completely, it looks like this. The oxide is somewhat like glass, so it should have a bit of transparency, which is why it looks like this overall. This is our interconnect, and of course there is oxide between these interconnects as well. The oxide actually extends all the way up here. It's all oxide. This is all oxide just to clearly show our metal structure. We hid the oxide above. So, using this 3D structure, we demonstrated the entire processing of a PMOS transistor and how we use the layouts and corresponding masks during this process. Now, let's take a look at an NMOS transistor, right? The process we just discussed was an example of PMOS, but actually, we are using NMOS technology now. NMOS technology means it includes both NMOS and PMOS, and since we are processing on the same P well, NMOS can be directly processed on the P well without any issues. However, PMOS must be processed in an N well. So let's take a look at the layout of this circuit structure and what the actual chip floor plan looks like. This here is our schematic diagram called schematic. As you can see, the schematic, which is essentially a type of circuit, looks like this. For example, this is a design for an inverter, right? This is an inverter circuit that functions in this way. Additionally, the schematic provides a comprehensive overview of the circuit's layout and operation, ensuring clarity in design. Its function is to take this input pulse and output a pulse that is inverted, making it an inverter device. Here's its schematic, and there's also something called a symbol. Later on, we'll talk about how, if you can use EDA tools to design this schematic and layout, there will be several views. Our schematic is usually presented in a schematic form, and this schematic will have a corresponding symbol. This means that when we call this schematic, we don't have to display the specific structure every time. Instead, this specific structure will have a symbol to represent it, and that symbol is the one for the inverter, right? Next, we have the layout. This is what the layout looks like. It's a multi-layer drawing. So, what is multi-layer? It consists of many layers, right? There are layers for poly, N-well, P-well, N-source, contact, and metal. So the entire layout looks like this. Actually, this part on the right is the layout for a PMOS. From the process flow we just discussed, I believe everyone should have an idea of what the PMOS layout looks like. First, we need to draw an end well, right? This blue part is the end well. We draw an end well, and inside the end well, what do? We first create an active region, making two active regions. One active region, represented by a dashed black line, is used to form our device, and the other active region is for forming the substrate contact. After we have the active regions, we need to create the polysilicon for the gate. This way we can form the gate. Next we have the source and drain injections, as well as the substrate contact injection. Note that the type for the substrate contact is N-type, while the source and drain injections are P-type. Then we connect them using contacts and metal. Since this is an inverter, the source of the PMOS needs to be connected to the substrate, so these two parts are connected with metal, right? Now, looking at the left side, we have the NMOS. The NMOS is directly processed on the P-type substrate, so we don't need to draw any wells. We just draw the active region and directly add the N-type injection outside the active region. Then, using polysilicon, the NMOS device on the left is formed. The NMOS substrate is P-type, so we need to do a P-type injection next to it. The source is connected to the substrate, which is grounded for the inverter, so these two can be connected together, and the NMOS and PMOS of the inverter are connected at the source. We can directly use the gate to connect the gates of these two devices with polysilicon. So this is the entire schematic symbol layout of the CMOS transistor, and its cross-section looks like this. It's important to pay special attention to this position and this position. These two are the substrate contacts, and we must not forget them. As I emphasized earlier, the MOS transistor is a 4-terminal device. I want to stress again that it is a 4-terminal device. When you're drawing, you must remember that there's also a substrate. You can't just forget about the substrate while you're drawing, as that could lead to issues with soft links, which we'll discuss in detail later. Now, let's take a look at design rule terminologies, which are some terms related to design rules. As we mentioned earlier, when we create layouts, we must adhere to the process design rules. These design rules contain some specific terms. Let's go through them. First, we have width. This is quite easy to understand. The symbol for it isn't very important because it may vary across different foundries in their design rule descriptions. What matters is the term width, which refers to a constraint on the width, or length of a shape. So, when I draw a shape, its edge length has certain constraints, which is represented by y. The second term is size. Note that size is a bit special in particular. When you first notice size, take note of the fact that its overall shape must indeed be a perfect square, and remember, it absolutely has to be a square. It can't be any other shape, it has to be a square. So when we say size is 0.2, it means it's a square shape with dimensions of 0.2 micrometers by 0.2 micrometers. What is this size used to constrain? Usually, it's used to constrain the contact, right? It's typically used to constrain the contact and the via, because in integrated circuits, the contact via is essentially a square hole, right? Represented by sense. Next, the third concept is spacing, which refers to the distance between two layers. This distance can be between layers at the same level or different levels. So there can be a distance between two layers at the same level, and there can also be a distance between different levels. The fourth concept is enclosure, which directly translates to wrapping. For example, enclosure of A beyond B means that A must wrap around B. What does that mean? It means that A is larger and can completely cover B, and the distance between the edges of A and B is what we refer to as enclosure, how much it wraps around. Next is extension. Extension means that the edges of two shapes are such that one shape's edge extends beyond the boundary of the other shape. Note that this extension is different from the enclosure we just talked about. In enclosure, the extension means that A completely covers B and extends beyond B to a certain degree. But for extension, it just means that if one edge extends out, it's considered an extension. It doesn't necessarily mean one shape covers or wraps around the other. The last concept is overlap, which refers to the degree to which two shapes overlap. So these data points help us understand the specific requirements more visually. We can look at a diagram. For example, in the first image, we draw a rectangle with a certain width and length. These dimensions are constrained by the y's parameters. For instance, if the y's parameter requires it to be equal to 1 micrometer, and I draw a width of 0.9 micrometers, then it doesn't meet the requirement. If I draw a width of 1.2 micrometers, then it meets the requirement. Typically, the requirement is for the minimum size, but sometimes it can also be for the maximum, depending on the specific needs. For example, if I draw a gate, the length of the gate is also represented by the y's parameters. Next, we have size.
As mentioned earlier, size must be a square, and it represents the length of the sides of the square, which is fixed. This is different from other parameters, which are usually a range. For example, the Y's parameter might say it must be less than 1 micrometer, so I could draw 0.8 or 0.9, and both would be acceptable. But size is different. It is equal to 0.2 micrometers, meaning it can only be 0.2. No other values are allowed. It is fixed. Now let's look at D, which refers to spacing.
The last concept is overlap, which refers to the degree to which two shapes overlap. So, overlap indicates how much they are overlapping. To better understand the specific requirements, we can look at a diagram. For example, in the first image, we draw a rectangle with a certain width and length. These dimensions are all constrained by the Y's parameters. If the Y's parameter requires it to be equal to 1 micrometer, and I draw a width of 0.9 micrometers, then it doesn't meet the requirement. However, if I draw a width of 1.2 micrometers, then it does meet the requirement. Typically, the requirement is for the minimum size, but sometimes it can also be for the maximum, depending on the specific needs. For instance, if I draw a gate, the length of the gate is also represented by the Y's parameters. Now, moving on to size. As mentioned earlier, size must be a square, and it represents the length of the sides of the square, which is fixed. This is different from other parameters, which usually have a range. For example, the Y's parameter might say it must be less than 1 micrometer, so I could draw 0.8 or 0.9, and both would be acceptable. But size is different. It is equal to 0.2 micrometers, meaning it can only be 0.2. No other values are allowed. It is fixed. Now, let's look at spacing. Spacing refers to the distance between shapes. You can see the distance between these two shapes, A and A, which are at the same layer. They can have distance requirements. Different layers can also have distance requirements. Some might wonder why there are distance requirements between different layers if they are at different heights. This is because, during processing, even though they are at different levels, the projected distance between them still has some constraints. This is represented by spacing. Next, we have size, right? Size. It's been mentioned that it must be a square, and it represents the length of the sides of the square, which is fixed. This is different from other parameters, which usually have a range. For example, the Y's parameter might say it must be less than 1 micrometer, so I could draw 0.8 or 0.9, and both would be acceptable. But size is different. It is equal to 0.2 micrometers, meaning it can only be 0.2. No other values are allowed. It is fixed. Now looking at D, what does D represent? It represents spacing, right? It refers to the distance. So you can see the distance between these two shapes, A and A, which are at the same layer. They can have distance requirements. Different layers can also have distance requirements. Some might wonder why there are distance requirements between different layers if they are at different heights. This is because, during processing, even though they are at different levels, the projected distance between them still has some constraints. This is represented by spacing. Next, we have enclosure. So what does it represent? It represents distance, right? You can see the distance between these two shapes, A and A, which are at the same layer. They can have distance requirements between them. As for different layers, there can also be distance requirements. Some might wonder if different layers are at different heights, why do they still have distance requirements? This is because during processing, even though they are at different vertical levels, the projected distance between them still has some constraints. This is represented by spacing. Now, moving on to enclosure. So, encapsulation means that A must cover B, and the edges of A should extend beyond the edges of B. Now, extension refers to A extending from B. B extending from A is this part. That's what we mean by extension. Finally, we have overlap, which is when A and B are overlapping. It refers to the overlap size. These terms often appear in design rules. It's because when you're reading the design rule documents, these symbols or terms will frequently come up, so you need to understand what kind of spatial relationship they represent between the graphics. A extends from B here, and B can extend from A. Overlap is when A and B overlap, indicating spatial relationships in design documents. Physical verification includes DRC and LVS. DRC checks design rules using EDA tools, comparing the GDS2 layout with rules to ensure manufacturability. LVS ensures layout matches the schematic, verifying connections with EDA tools using the GDS file and netlist. Design rules define spatial relationships in graphics. Physical verification includes DRC and LVS. DRC ensures design rules are followed using EDA tools, checking geometric shapes in the GDS2 file. LVS compares layout to schematic, verifying device connections. Both checks ensure design accuracy. Now, let's introduce physical verification. Earlier, when we talked about the design process for digital circuit layouts or analog circuit layouts, we mentioned DRC and LVS, which are part of physical verification. Let's take a closer look at what these two verifications do. First, DRC, which stands for Design Rule Check. From its name, you can understand that it's about checking design rules. Design rule check is necessary because the design rules contain a lot of constraints regarding the sizes and distances of geometric shapes. We can't rely solely on ourselves to ensure that everything is correct. While drawing, we might think we're following the rules, but there could be mistakes. Ultimately, we need tools, specifically our EDA tools, to check whether the graphics we've drawn meet the requirements of the design rules. How does this work? There's software that takes two inputs. One is the GDS2 file, which is our layout file, and the other is the design rules, which generate a set of checking rules. By inputting these two files into the software, we can perform a DRC check. The software checks whether the geometric shapes in your GDS2 file comply with the requirements in the design rules. If they don't, it will highlight issues like incorrect widths or distances. This DRC check is essential to ensure that your GDS2 file corresponds to the requirements for manufacturability. If you don't meet these basic requirements, your chip will definitely fail during fabrication. Next, we have LVS. After passing DRC, you need to perform LVS, which stands for Layout versus Schematic. As the name suggests, it's about comparing the layout to the schematic. The purpose is to check whether the connections of the devices in your layout match those in your schematic. When you draw the layout, you definitely refer to your schematic for the connections. For example, if you have a transistor, you connect the source and drain according to the schematic. However, during the drawing process, you might make a mistake and accidentally connect the gate to the source instead. That would create a mismatch between your layout and schematic, leading to problems. In other words, your layout wouldn't represent what was originally intended in the schematic. Therefore, this check must also be done using EDA tools to ensure that your layout matches the original design in the schematic. The inputs for this check also include your layout, which is the GDS file, and you also need to input your netlist, which corresponds to your schematic. The software will then check whether the netlist generated from the GDS2 file matches the netlist from the schematic. If they match, great. If not, it will indicate that there are issues, such as problems with the device connections or short circuits. You will then need to correct your layout until the LVS check passes. Once LVS passes, it indicates that your layout accurately reflects your original design. If both of these steps pass, you've completed a preliminary check of your layout. You input your schematic, right? The netlist corresponding to the schematic, and then it can check your GDS2. From the GDS2, it will also generate a netlist, and then these two netlists will be compared to see if they match. If they match, great, no problem. If they don't match, it means you've made a mistake in your drawing. It will prompt you, indicating whether there's an issue with the device's width ratio, a problem with your device connections, or if there's a short circuit. You'll then need to correct your layout until your LVS passes. Once LVS passes, it indicates that your layout accurately reflects your original design. If both of these steps pass, you've completed a preliminary check, which is a basic verification of your layout. So the next thing we're going to talk about is post-simulation, right? We've mentioned post-simulation before, and it's a very important aspect. Why is it so important? Because it can largely help us check the quality of our layout, especially for analog circuit layouts. Why do I say that? Let's take a look at the left side here, which shows a schematic, for example, a very simple differential amplifier. The schematic is quite straightforward with just 5 components, 3 MOSFETs and 2 PMOS transistors, along with some connections. This is our schematic, and it's very simple. The connections in the schematic are all ideal connections. For instance, the drain of this transistor connects to the drain of that transistor, which is the Vout negative line. This is an ideal wire, right? All the nodes here are ideal, meaning there are no parasitics involved. This is an ideal scenario. However, once we finish drawing the layout, the metal lines are definitely made up of different layers of metal. When we introduced the cross-section of the chip earlier, we could see that there are parasitics between these metal lines. So once parasitics are present, the actual situation might look something like this, illustrative. it not only has parasitic capacitance, but also parasitic resistance, right? Because the metal lines used for connections cannot have zero impedance. They can't be superconductors. They will have parasitic resistance. So, there are parasitic resistances within the wires, and between the wires, there are parasitic capacitances. This makes the whole situation quite complex, with a lot of parasitic components involved. Once we add these parasitic components, the characteristics of the circuit become uncertain. That's why we need to do post-simulation. This is why post-simulation is important. First, we need to perform something called PEX, which stands for parasitic extraction. So how do we do this? We take our GDS2 file, the one we've drawn, and then we can generate parasitic parameters through parasitic extraction. After that, we take our original netlist and annotate it with the parasitic parameters. So our initial netlist looks like this, right? After adding the parasitic parameters, this process is called back annotation. Once annotated, the netlist might look something like this, becoming much more complex with a lot of parasitic resistances and capacitances appearing. Then we perform a simulation on this, which is called post-simulation. This post-simulation can reflect all the parasitic effects in our layout. If the post-simulation passes, it indicates that our layout is acceptable. If it doesn't pass, then we definitely need to modify our GDS2 or adjust the layout. However, the capabilities of post-simulation are also limited. There are some non-ideal effects that post-simulation cannot account for, such as device mismatches caused during the fabrication process. So, it does have its limitations, but at least it can simulate the various parasitic effects and characteristics of our interconnects. If your post-simulation is all good, it means your layout should be fine. We're almost done here. So in this last part, I just want to give you a little bit more detailed overview of the various tools that are commonly utilized in the field of layout design, which we call EDA tools. The two main tools come from these two companies. The first one is KEDS, which has an IC design platform. So in this IC design platform, there is specifically a dedicated layout design tool, known as the What You Also Layout Editor. We use the IC618 design platform, which supports software embedding, layout editing, and simulation. My simulator is Spectrum. For physical verification, we use Calibre from Mentor Graphics, now Siemens, for DRC, LVS, and PEX. Calibre integrates with IC618 for analog design. The software runs on Linux. Start IC511 with ICFB and an IC615 Plus with Waterhouse N. The interface is similar across versions, featuring file, tools, and options. The library manager in Tools manages design directories, libraries, and key elements like spectrum, symbol, and layout. It can embed this spec into the IC618, and then we can do the pin placement. When I heard about this, we need to do the layout design here. For physical verification, we use software from Mentor Graphics. Of course, Mentor has now been acquired by Siemens. So, Mentor has a software called Calibre, which can perform the LVS we just mentioned, like DRC, LVS, and PEX. It can handle all of that. At the same time, Calibre can also be embedded into the IC618 platform. This is basically the software we use for analog design. Now let's take a look at the interface of this software and give a brief introduction. The version used in this screenshot is quite old. We just talked about IC618, but actually this is IC5141, which is an older version. All of this software is installed on a Linux platform, so they all run in Linux. To start it, you need to open a terminal in Linux and enter the startup command for the software. For IC511, the command is ICFB. ICFB is the startup command followed by a space and an ampersand. What does this mean? The ampersand is a Linux system usage that indicates it will run in the background. Running in the background means that if you close the terminal, the software will not close. Otherwise, if the software is bound to the terminal and you accidentally close the terminal while running in the foreground, the software will close as well. Generally, we run it in the background. For IC615 and above, the startup command is Waterhouse. And you just add a space and then the ampersand. This is for IC 615 and above. Once opened, the interface looks something like this. Even though there are some changes in the IC 615 interface, they are quite similar. After opening, it looks like this. The interface is not large. First, there are three options: File, Tools, and Options. Let's take a look at the Tools section. When we click on Tools, we will find something called Library Manager. The Library Manager is very important as it manages our entire design directory. Once opened, it has three columns. The first one is Library, where there are many design projects. Each library contains many cells, which are various electronic units. Under each cell, there are different wheels, and the most important ones are spectrum, symbol, and layout corresponding to the schematic. Then you just add a space and press enter, and that's it for IC 615 and above. Once you open it, the interface generally looks like this. Even though there might be some changes in the IC 615 interface, they are quite similar. After opening, it looks something like this. The interface isn't very large. First, there are three options: File, Tools, and Options. Let's take a look at the Tools section. When we click on Tools, we will find something called Library Manager. The Library Manager is very important as it manages our entire design directory. Once opened, it has three columns. The first one is Library, where there are many design projects. Each library contains many cells, which are various electronic units. Under each cell, there are different wheels, and the most important ones are spectrum, symbol, and layout corresponding to the schematic. The symbol and the schematic are quite important. These three are essential